Welcome back to the deep dive. We're doing something a little different today. We're shifting our whole perspective.
It's a pretty big shift,
A
actually.
huge one. If you've been with us for the previous episodes in this biochemistry series, you know we've been acting a lot like forensic analysts.
Right. Examining the evidence after the fact.
Exactly. We've been looking at crime scenes that are frozen in time. We've examined the structure of DNA. We've looked at the beautiful twist of a protein helix. We've looked at enzymes just sitting there like statues. It's all been very, well, static.
That's a very fair description. Structural biochemistry is, at its heart, the study of the parts list. It's like taking a car engine apart and laying every single screw, piston, and wire on the garage floor.
Yeah.
You know what everything is, you know what it's made of, but you don't necessarily know how it all works together. You don't know how it drives.
But today, we're putting the key in the ignition. We are watching the engine turn over. We are finally diving into metabolism.
We're watching the crime scene in motion.
Yes. And to kick this off, I want to start with a really evocative image from one of our primary sources, Leninger's Principles of Biochemistry.
A classic.
The text references Antoine Lavoisier, the famous 18th century French chemist. He looked at a living animal, I think it was a guinea pig, in his experiment, and he compared it to a burning candle.
The torch of life. It's one of the most powerful and enduring metaphors in all of science.
The torch of life. Lavoisier basically said, look, respiration is nothing but a slow combustion of carbon and hydrogen. He had this amazing insight that fundamentally a living thing and a lighted lamp are doing the exact same thing.
They're taking in fuel, they're taking in oxygen, and they're releasing energy.
And releasing energy. But here is the mystery that really hooked me. And it's the question that's going to drive this whole deep dive. If I am essentially a burning candle, why don't I just go up in flames? How do I burn fuel to stay alive without incinerating my own cells?
And that is the central question of bioenergetics. It's the difference between, say, a forest fire and a steam engine. One is just chaotic, uncontrolled release of energy.
Right. Chaos.
The other is controlled. It's harnessed. It's work. Lavoisier was brilliant because he identified the inputs and the outputs. He knew we consumed oxygen and fuel, and he knew we produced heat and carbon dioxide. But he didn't know the mechanism. He had no idea how we tamed that fire.
And that's our job today. And just to be clear for everyone listening, this is our synthesis. We're combining the systems-level physics from Leninger, which really explains the why, with the clinical, gritty reality of Harper's Illustrated Biochemistry, which explains the how.
Right. This isn't a replacement for reading the books. You have to read the books. Think of this as a guided tour, a conceptual map to help you navigate those dense, beautiful texts.
Exactly. So today, we're going to look at the economy of the human body.
And economy is absolutely the right word. I want you to really hold on to that concept. Metabolism is so often taught as just a long, boring list of chemical equations and pathways, which, frankly, is why so many students hate it.
The spaghetti diagrams.
The spaghetti diagrams, exactly. But it's not a list. It is a market. It's about supply and demand. It's about currency exchange, resource allocation. You have a limited amount of fuel coming in, carbohydrates, lipids, proteins, and you have constant demands.
Building new cells, moving your muscles, even just thinking your thoughts right now.
All of it costs energy. And the body has to make these split-second, incredibly sophisticated decisions on where to spend that energy.
And just like a real economy, if that regulation fails, you get a recession or, full-blown depression.
Exactly. In the body, we just call that disease. Starvation is a supply shock. Diabetes is a catastrophic regulatory failure.
So let's introduce our detective persona for this part of the series. Up until now, we've had the forensic analyst looking at the static DNA fingerprints. Now, we need Medlock Holmes to step back and watch the whole city in motion. We're moving from static biochemistry to dynamic biochemistry. So what's our mission for today's deep dive?
Our mission is to understand the flow. We need to map out the rules of the game, which are basically the laws of thermodynamics. Then we need to understand the currency we use to pay for everything that's ATP.
Okay.
Then we need to look at the market itself, how we trade glucose, fat, and protein between different organs. And finally, we have to look at what happens when that market crashes.
Sounds like a plan. So let's start with those rules of the land. Part 1, bioenergetics and thermodynamics. I want to go right back to that burning candle analogy. When I put my hand over a candle flame, I feel heat. A lot of it.
Sure.
And something like a steam engine, it runs on heat, right? It boils water, creates steam pressure. That pressure pushes a piston. Is that us? Are we just very complicated, squishy steam engines?
No. And this is a really critical distinction that Leninger makes right out of the gate, and it's one that people often get wrong. Cells are isothermal.
Isothermal, meaning
Yeah.
constant temperature.
Constant temperature. Right. Think about how that steam engine works. It relies on a temperature gradient. You have a very hot boiler and a cooler condenser. Heat flows from the hot part to the cold part, and you capture that flow to do work.
Okay, that makes sense.
But a cell is microscopic. It's roughly 37 degrees Celsius or 98.6 Fahrenheit everywhere inside it. There's no hot side of a mitochondrion and a cold side. It's all the same temperature.
So if I were to release a massive amount of heat in one part of the cell, like a tiny chemical explosion, it wouldn't push a piston or turn a wheel.
No, just cook the machinery, you denature the proteins, you'd essentially hard-boil the egg. So living systems cannot use heat as their primary source of energy for work.
So we have a big problem. We are burning fuel, which we know releases energy, but we can't use the heat from that burn. So what do we use?
We use Gibbs free energy, which is usually denoted as the letter G.
Okay, I can almost feel the listeners tensing up. High school physics flashbacks are kicking in. But let's break this down, because Leninger explains it in a way that is actually really intuitive. If we aren't heat engines, what kind of engines are we?
We are chemical engines. We run on chemical potential energy. And to get a handle on this, we really have to look at the two great laws of thermodynamics.
Okay.
The first law is the easy one, conservation of energy. You can't create it, you can't destroy it, you can only transduce it, you can only change its form.
So when you eat a burger, the chemical energy stored in the bonds of that meat and bread is converted into other things.
Right. It's converted into the kinetic energy of motion, into electrical gradients in your brain that form thoughts, and yes, eventually a lot of it is lost as heat. But the total amount of energy in the universe remains constant.
Simple enough, but it's the second law that always feels a bit existential, the law of entropy.
The second law. It states that the universe as a whole always tends toward disorder. Entropy, which is just a measure of randomness or disorder, is always increasing.
If you leave a house alone for 100 years, it falls apart.
Right.
The roof caves in, the paint peels, the wood rots. It doesn't spontaneously assemble itself into a beautiful mansion.
Exactly. Chaos is the default state of the universe.
And yet, and this is the paradox of life that Leninger talks about, I am not falling apart. Well, hopefully not yet. I am an incredibly ordered structure.
You have a ridiculously ordered structure.
I have DNA wrapped specifically around histones. I have proteins folded into perfect functional shapes. If the universe wants chaos, how does life even exist? Are we breaking the law?
We're not breaking the law, we're finding a loophole. Or maybe a better way to put it is, we are paying a tax. This is the crucial concept. Living systems are what physicists call open systems. We maintain our internal order, our low entropy, by exporting disorder to our surroundings.
Okay, explain that. What does it mean to export disorder?
Think about what you do every single day. You take in complex, highly ordered food molecules, proteins, starches, fats, very ordered. You extract the energy from them to maintain your own structure. And then what do you release?
Carbon dioxide and water.
Right. Small, simple, scattered molecules. You breathe them out, you scatter them into the atmosphere, and you radiate heat. Heat is the most disordered, chaotic form of energy there is. It's just molecules vibrating randomly.
So I'm staying organized by making the room around me messier.
Precisely. You are an entropy-generating machine. Your job, from a thermodynamic perspective, is to create a tiny, beautiful island of order by polluting the rest of the universe with chaos. As long as the total entropy of you plus your surroundings increases, the second law is perfectly happy.
This brings us to that famous equation that everyone sees in textbooks. Delta G, delta H, T delta SA. I know we promised not to do a lot of math, but we have to understand what this means conceptually.
We do. It's really the accounting sheet for everything we just discussed. Delta G is the Gibbs-free energy. That's the energy that is actually available to do useful work.
The profit.
The profit, exactly.
Yep.
Delta H is enthalpy. You can think of that as the total heat content in the chemical bonds, the gross revenue. And then the last term, T delta S, is the temperature times the change in entropy. That's the tax. That's the energy you have to lose as disorder to make the universe happy.
So put simply, the energy I can actually use to build things, delta delta, is equal to the total energy released from my fuel, delta H da, minus the tax I'm forced to pay to the universe in the form of disorder.
That is a perfect summary. If you don't pay the entropy tax, the reaction just doesn't happen. And this simple equation tells us It's negative, the reaction is exergonic.
Exergonic, meaning it gives off energy.
It gives off free energy. It's downhill. It happens spontaneously, like a ball rolling down a hill.
And if the delta G is positive,
It's endergonic. It's an uphill reaction. It requires a net input of energy. A ball does not spontaneously roll up a hill.
but wait a minute, life is full of uphill battles. Building a protein from individual amino acids is a hugely uphill process. Creating a DNA strand is uphill. If the universe only wants to go downhill, how do we build anything at all?
We cheat. Well, chemically speaking, we couple. This is probably the single most important concept in all of bioenergetics. Leninger emphasizes this over and over. Cells make impossible endergonic reactions happen by coupling them to highly favorable exergonic ones.
Give me a visual for coupling. How does that actually work?
Okay, imagine a gear system. You have a small gear that needs to turn counterclockwise to lift a heavy bucket of water up from a well. That's your protein synthesis. It's an endergonic uphill task. It's too heavy. It won't move on its own. Gravity wants it to stay down.
Right. Positive delta G hour.
But right next to it, meshed with it, you have a massive flywheel that is spinning clockwise with incredible force.
And that's the exergonic reaction, the downhill one.
Right. Let's say that flywheel is being driven by a huge boulder rolling down a mountain. The massive spontaneous force of the boulder rolling down, exergonic, can overpower the resistance of the bucket, endergonic, and pull it up.
As long as the energy released by the boulder is more than the energy needed to lift the bucket.
Precisely. We just add the delta G values together. If the sum of the two reactions is negative, the whole system proceeds. We use the energy from a controlled crash to drive a construction project.
So in the human body, what is that massive flywheel? What is the boulder we use to drive almost everything else?
That brings us to part 2, the currency of the realm. And that currency is ATP, adenosine triphosphate.
The universal energy carrier.
The universal currency.
Okay, I want to challenge this for a second. We always hear ATP is the energy molecule. But Leninger points out something really interesting. A molecule of glucose has way more total energy packed into it than a molecule of ATP. A molecule of fat has vastly more.
Oh, orders of magnitude more.
So why don't our enzymes just accept glucose directly as payment? Why do we have to go through this intermediate step of converting everything into ATP first? Seems, inefficient, like a weird middleman.
It's about standardization and what we call phosphoryl group transfer potential. Think of a molecule of glucose like a gold bar. It has a tremendous amount of value, but you can't walk into a coffee shop and buy an espresso with a gold bar.
Right, they'd look at you funny.
You need cash. You need small, standardized, denominated units that every machine in the cellular economy accepts without question. ATP is the $5 bill of the cell.
So it's not about the total amount of energy, it's about having it in a usable, transferable packet.
Exactly. It's energy in a form that is ready to be spent.
But chemically, why ATP? What makes it so special? In every textbook, we see it drawn with that little squiggly line next to the last phosphate group, the famous high-energy bond.
Ah, the high-energy bond. That term is actually a bit of a misnomer, and Leninger's very, very careful to correct this misconception.
Wait, you're telling me the bond itself isn't high energy?
I'm telling you that breaking any chemical bond never releases energy. That's a fundamental law of physics. It always takes energy to break a connection. Think about snapping a stick in half. You have to put effort in to snap it. The energy doesn't come from the break itself.
So where does it come from? If breaking the bond costs energy, where does the explosion of ATP hydrolysis come from? Why is it worth so much?
It comes from the fact that the products, the pieces left over after the break, ADP and inorganic phosphate, are drastically more stable and lower in energy than the original ATP molecule was. The ATP molecule is under immense chemical stress.
It's an unstable molecule.
It's incredibly unstable. Leninger lists 3 specific chemical reasons for this, and they really explain the why of bioenergetics. It's worth walking through them.
Okay, let's do it. Reason number 1.
Charge repulsion. If you look at the structure of ATP, you have a chain of 3 phosphate groups all linked in a row. Each of those phosphate groups carries a strong negative charge.
And like charges repel each other.
They repel each other violently. Imagine taking 3 powerful magnets, forcing their north poles together, north to north to north, and then trying to hold them together with a piece of tape. That tape represents the chemical bonds in ATP. The molecule is literally vibrating with the tension of those negative charges trying to fly apart.
So it's a coiled spring. It's just waiting to be released.
It is a loaded chemical spring. So when an enzyme brings in a water molecule to hydrolyze ATP, when it cuts that tape, that terminal phosphate group shoots off. And that massive relief of electrostatic tension releases a huge amount of free energy.
Okay, that's intuitive. What's reason number 2?
Resonance stabilization. This one's a little more subtle. It's more about electron happiness. In a free phosphate molecule that's just floating in water, the electrons associated with it can float around or delocalize over multiple oxygen atoms. They have a big yard to play in.
Electrons like having space.
They love having space, but when that phosphate is locked into the ATP chain, the electrons are confined. They're pinned down in less favorable positions. They can't resonate as freely.
They're claustrophobic.
That's a great way to put it. So when you cleave the ATP, you liberate that phosphate. The electrons can immediately spread out over the whole molecule again. The molecule exhales, chemically speaking, and that relaxation into a more stable state releases energy.
Okay, charge repulsion, resonance stabilization. And reason 3.
Solvation, or hydration. It's just a fancy way of saying that the products, ADT and the free inorganic phosphate, bind much better to the surrounding water molecules than the original ATP molecule did. The universe prefers the wet version of the broken parts.
So let me see if I've got this. The magnets are pushing the phosphates apart, the electrons want to spread out, and the water molecules are waiting to grab the pieces.
You've got it. You put all 3 of those forces together, and the result is a massive spontaneous release of free energy. The standard delta G is about negative 30.5 kilojoules per mole. That's a huge energetic payoff.
Okay, so ATP is this coiled spring, it's this loaded gun, it's desperate to explode. But here is where I get confused again. If it's so desperate to release its energy, why doesn't it just pop the moment it's made? Why don't our cells just, heat up and boil from all this ATP spontaneously breaking down in water?
That is the absolute beauty of it. And this is a concept called kinetic stability. ATP is thermodynamically unstable, meaning it wants to break down, but it is kinetically stable.
Explain that distinction for me. Thermodynamically unstable versus kinetically stable.
Okay, think of a massive boulder perched right at the very edge of a high cliff. It has enormous potential energy. It wants to fall. That's thermodynamic instability.
Right, gravity's pulling on it.
But there's a little lip of rock, a small ridge, holding it back. It won't fall unless you give it a specific push to get it over that ridge. That little lip of rock is the activation energy barrier.
So the boulder just sits there, safely storing all its potential energy until something comes along and pushes it over the edge.
Correct. In the cell, ATP sits there, vibrating with all that chemical potential, but it won't break down unless an enzyme is there to lower that activation energy barrier, to essentially chip away that little lip of rock.
This is brilliant. So the money is safe in the bank. It won't just vanish from your account. You need the authorized signature, which is the specific enzyme, to make a withdrawal.
Precisely. This allows the cell to regulate its energy flow with exquisite control. If ATP just broke down on its own, all that energy would be released as useless waste heat. Because it requires a specific enzyme, the cell can control exactly when and where that packet of energy is released and for what purpose.
There's one more misconception I really want to clear up, something I learned from the Leninger text. We always say ATP hydrolysis releases energy. So we get this picture in our heads of the ATP breaking, releasing a puff of heat, and that heat somehow making a muscle move or a reaction go.
Right.
But we already established that we aren't heat engines. So how is the energy from ATP actually used?
We almost never just hydrolyze ATP into heat. That would be incredibly wasteful. Instead, we use a mechanism called group transfer. I like to call it the hot potato concept.
The hot potato concept. Walk me through that.
Okay, let's take the very first step of using glucose in a cell, the first step of glycolysis. We need to energize the glucose molecule to get it ready for the subsequent steps. We don't just break an ATP molecule next to the glucose and hope the heat helps it along. No. An enzyme, hexokinase, grabs both the ATP and the glucose. It takes that high-tension terminal phosphate group from the ATP, the one that's desperate to leave, and it directly smashes it onto the glucose molecule.
So now the glucose itself has the phosphate attached to it.
Yes. We've made a new molecule called glucose-6-phosphate. And because that phosphate group is still so stressed out and high energy, now the entire glucose molecule is stressed out. It's now a higher energy molecule, it's unstable, it's primed for the next reaction. It's the hot potato.
So we didn't just burn the money for warmth, we invested it. We transferred the instability from the ATP directly to the substrate we wanted to work on.
Exactly. We used ATP to raise the energy level of the worker so the worker could then go on to do its job. It's a much more elegant and efficient system than just making heat.
Okay, so we have the rules of the land, which is thermodynamics, and we have the currency, which is ATP. Now let's talk about the market. This is where we really bring in Harper's biochemistry. We aren't just single cells floating in a pond. We are a complex, multicellular organism, and we trade in three main types of fuel.
Right. This is where we get into the physiology, the big three. Carbohydrates, which for us primarily means glucose, lipids, which means fatty acids and ketone bodies, and proteins, which are made of amino acids.
And Harper frames this beautifully as a constant cycle between two states, anabolism and catabolism.
Think of anabolism as construction. It's characteristic of the fed state. You've just eaten a meal, you have an excess of resources coming in, so you're building things. You're building proteins, you're storing fuel. This requires an input of ATP.
And catabolism.
Catabolism is the opposite. It's demolition. It's characteristic of the fasting state. You're breaking down complex molecules like stored fat or glycogen to generate ATP.
And there's a phrase in Harper that I found really interesting. It's so simple. You burn what you eat.
It sounds like a slogan from a diet book, but it's a profound biochemical fact. We can actually measure this in a lab using something called the respiratory quotient, or RQ. It's a ratio of the carbon dioxide you breathe out to the oxygen you breathe in.
And what does that ratio tell us?
It tells us exactly what kind of fuel your body is burning at that moment. The chemistry is different for burning carbs versus fats. If you eat a meal of pure carbohydrates, your RQ will be 1.0. Your entire metabolic machinery shifts to prioritize burning those carbs.
What if I switch to a high-fat, low-carb diet?
Your RQ will drop to about 0.7. The machinery literally adapts. It changes the expression of certain enzymes to become better at burning fat. The body is incredibly flexible.
But not all animals have the same flexibility. Harper throws in this really fun fact about cows, about ruminants. They don't run on glucose like we do they?
Not at all. And it's a great example of metabolic diversity. When we eat a sandwich, our blood glucose spikes and insulin comes out. A cow eats grass, which is mostly cellulose, but the cow itself can't digest cellulose. The bacteria living in its rumen, its first stomach, digest it for it.
Through fermentation.
Exactly. The bacteria ferments the grass into what are called short-chain fatty acids, things like acetic acid, propionic acid, butyric acid. Acetic acid is just vinegar. The cow absorbs these fatty acids directly into its blood.
So a cow is essentially running on vinegar and other fermentation products.
That's right. Their blood glucose levels are incredibly low compared to ours, yet they build massive amounts of muscle and produce milk, which is full of the sugar lactose. It just shows that metabolism isn't one rigid universal pathway. It's a set of adaptable solutions to the problem of getting energy.
Fascinating. But let's stick to humans. We have this daily cycle of feasting and fasting. I think walking through a day in the life of our metabolic economy is the best way to visualize all of this. Let's say I've just eaten a massive bowl of pasta. I'm in the fed state. What is happening in the market?
The floodgates have opened. A torrent of glucose is pouring from your gut into your bloodstream. Your pancreas senses this spike in sugar and releases the hormone insulin.
And insulin is the CEO during the economic boom times?
He is the master regulator. Insulin sends out a company-wide email, and the subject line is, "Build and store, times are good."
So what are the specific priorities in that email?
Priority 1, stop making fuel we don't need. The liver immediately shuts down its own glucose production. Why make it when we have plenty coming in from the outside?
Makes sense.
Priority 2, burn the cheap stuff. All the tissues in the body, especially muscle and fat, are told to switch to burning glucose because it's everywhere and it's easy to use. Priority 3, save the rest for later.
Where does the excess glucose go?
First, the liver and muscles top up their glycogen stores. Think of glycogen as your checking account. It's for quick, easy access cash, but the account has a limit. You can only store so much.
And once the checking account is full?
Once the glycogen stores are full, the liver starts a process called de novo lipogenesis. It takes the rest of that sugar and turns it into fat triglycerides. This fat is then packaged up and shipped out to the adipose tissue.
That's the savings account.
That's the long-term savings account. And what about protein? What's happening there?
Protein synthesis ramps up. Harper makes a great point that building proteins is incredibly energy expensive. It takes a huge amount of ATP to link all those amino acids together in the right order. So you only do a heavy construction like that when energy is cheap and plentiful.
Right. Something like 20% of your resting energy expenditure after a big meal goes just to building and turning over proteins.
Okay, so that's the party, that's the feast. But then I go to sleep, It's 3:00 a.m. I haven't eaten in 8 hours. The pasta is long gone. We now enter the fasting state. The economy starts to tighten up.
It does. Blood glucose levels start to fall. As they fall, insulin levels drop. Now, a new hormone takes the stage, glucagon, which is also released from the pancreas. Glucagon's email subject line is, austerity measures, conserve and produce.
Who gets their budget cut first?
The muscles and the fat cells. They are told to stop using glucose. The prime directive from glucagon and low insulin is, leave the glucose for the brain.
Why? Why is the brain so special? It seems a bit selfish.
It is selfish. And this brings us to part 4, the trading partners, the different organs. I really like how we decided to personify the organs in our prep for this. Let's start with the brain.
The diva.
The diva is perfectly accurate. The brain represents only about 2% of your total body weight, but it consumes a whopping 20% of your resting energy. It's incredibly metabolically active.
And it's picky eater.
An incredibly picky eater. Harper really emphasizes this point. The brain has almost no capacity to burn fatty acids directly for fuel.
Why not? Fat is a fantastic fuel. It's so energy dense, the muscles love it.
They do. But fatty acids are large, greasy molecules. In the blood, they have to be chauffeured around by a big protein called albumin. They're bulky. They cannot easily cross the highly selective blood-brain barrier.
But the brain is protected, but it's also isolated. It's behind a velvet rope at a nightclub.
It is. So while your muscles are happily burning fat during a fast, the brain is screaming, "Where is my glucose? I only eat glucose."
So the entire rest of the body has to work together to keep the diva happy.
Exactly. This is the entire logic of the fasting state. And the hero of this story is the liver. The liver completely flips its function. Instead of being a glucose consumer, it becomes a glucose producer. It starts by chopping up its stored glycogen, that's glycogenolysis, to release sugar back into the blood.
And what about the adipose tissue, the savings account?
The bank vault swings open. Adipose tissue is not just passive insulation, it's not bubble wrap, it's a dynamic endocrine organ and a bank. It starts breaking down its stored triglycerides in a process called lipolysis. This releases 2 crucial things into the blood, fatty acids and glycerol.
And where do they go?
The fatty acids go everywhere else. They go to the heart, the kidneys, the skeletal muscles. All those organs say, okay, we'll switch to burning this oil so we can save the high-octane gasoline, the glucose for the brain.
And the glycerol.
The glycerol, which is the 3-carbon backbone of the fat molecule, goes to the liver. And the liver is amazing. It can take that glycerol and, through a new pathway, turn it into brand new glucose.
Which brings us to the liver. You called it the altruistic banker.
It really is. The liver is the most metabolically flexible organ in the body, but it's remarkably selfless. In the fasting state, it works overtime to make glucose via gluconeogenesis. Literally, new glucose creation, not for itself, but to export it into the blood to keep the brain and red blood cells alive. It essentially cooks the food, but serves it to everyone else at the table.
Does it use any of the fat for itself?
It burns fatty acids to power the machinery to make the glucose. So it's burning fat to make sugar. And here's a key detail from Harper that is so important clinically. The liver also takes those fatty acids and synthesizes ketone bodies. But, and this is the kicker, the liver itself cannot use ketone bodies as fuel.
Wait. It makes them, but it can't eat them.
Correct. It lacks a specific enzyme, a transferase, that's required to activate and break down ketone bodies. It produces ketones solely for export to the peripheral tissues. It's a soup kitchen that doesn't eat its own soup.
Incredible. Okay, then there's skeletal muscle, the versatile worker.
Muscle is the blue-collar engine of the body. It does whatever is needed. At rest, it's happy to burn fatty acids. When you're active and sprinting, it burns glucose or its own stored glycogen for quick energy. But in prolonged starvation, it's forced to make a terrible sacrifice.
What's the sacrifice?
It is the body's main protein reservoir. If the brain is desperately screaming for glucose and the liver has already run out of glycogen, the muscle receives a hormonal signal to start breaking down its own contractile proteins. It tears down its own walls to release amino acids into the blood,
Which then travel to the liver.
to be turned into glucose. It is effectively burning your furniture to heat the house. It's a last-ditch, desperate measure to keep the brain alive.
Finally, there's one group I often forget about, but Harper says they are critically important. The erythrocytes. the red blood cells. You call them the minimalists.
What are the ultimate minimalists? In order to make as much room as possible for hemoglobin to carry oxygen, mature red blood cells got rid of all their organelles. They chucked out their nucleus. And crucially, for our story, they have no mitochondria.
No mitochondria means no Krebs cycle, no electron transport chain. They can't burn fat. They can't even use oxygen for energy.
Correct. They are swimming in a sea of oxygen, but they can't use it for their own energy needs. They are strictly anaerobic organisms. They rely 100% on taking glucose and doing anaerobic glycolysis. They take glucose, break it into lactate, and spit the lactate out into the blood.
So they are wholly dependent on the liver maintaining blood sugar at all times.
100%. If blood glucose drops to 0, red blood cells die. If red blood cells die, oxygen transport stops and you die very quickly. That's why maintaining blood sugar isn't just a good idea, it's a matter of life or death.
This leads perfectly into part 5, regulation. How does the body maintain this delicate balance? Linenger makes a very almost philosophical point here about the difference between equilibrium and steady state.
This is a concept that can really blow students' minds when they first encounter it. We tend to think equilibrium is a good thing. It sounds balanced, peaceful, but in biology, equilibrium, death.
Explain that. Why is equilibrium so bad?
Equilibrium, by its chemical definition, means the forward reaction and the backward reaction are happening at the exact same rate. There is no net flow. The free energy change, the delta G, is 0. And if delta G is 0, you cannot do any work. A battery at equilibrium is a dead battery.
So life isn't about being in balance.
Life is about being in a dynamic, steady state.
Give me an analogy for that.
Okay, imagine a river. You're standing on the bank, and you notice that the water level stays constant all day long. It looks stable. That's the steady state. But is the water in the river still? No. It is rushing through furiously. Water is constantly coming in from the mountains upstream and constantly flowing out to the sea downstream.
It's the flow that has the power.
Exactly. It's the flow that allows the river to turn a water wheel and do work. If you were to dam the river at both ends and stop the flow, the water would become a stagnant pond. That is equilibrium. The pond scum grows. The work stops. We stay alive by keeping all of our metabolic reactions far away from equilibrium. We are constantly feeding fuel in and taking waste out to keep that wheel turning.
So how does the cell control the flow of this river? Leninger talks about certain reactions being bottlenecks.
Right. Most of the chemical reactions in our cells are very fast and easily reversible. They're like wide, slow parts of the river. But in every pathway, there are 1 or 2 enzymes that are very slow and whose reactions are highly exergonic and essentially irreversible. They are the bottlenecks, the narrow rapids.
Why would we want bottlenecks in our system? That sounds inefficient.
Because bottlenecks are control points. If you want to control the flow of the entire river system, you don't build a massive dam along its entire length. You build one dam at the narrowest, fastest point. In glycolysis, for example, the enzyme PFK1 is a major bottleneck.
Phosphofructokinase 1, a famous one.
The most famous one. Because it's the main bottleneck, the cell puts all its complex control mechanisms there. It's regulated by ATP, by citrate, by a dozen other molecules. If you want to speed up your entire metabolism, like when you see a tiger and need to run, you simply open that one valve a little wider. You don't have to regulate every single step, just the key bottlenecks. And this is where hormones like insulin and glucagon come in. They are basically the engineers in the control room twisting the dials on these bottleneck enzymes.
That's homeostasis in a nutshell. Keeping the river level constant, which is your blood glucose at about 5 millimolar, by constantly adjusting the rate of release at the main dams.
But sometimes the regulation fails, the judgment falters, or the environment pushes the entire economy too far. And that brings us to part 6, when the judgment falters, the clinical context.
This is where we see the tragic consequences of breaking these biochemical rules. Let's start with a simple but brutal example: starvation.
Harper lays out a timeline that is terrifyingly precise. Let's say I stop eating completely. I'm lost in the woods with only water. What happens at the 18 to 24-hour mark?
By about 18 hours, your liver glycogen is gone. The short-term checking account is officially overdrawn. Now, your body is fully dependent on gluconeogenesis. The liver has to make new sugar from scratch.
Using those amino acids from muscle breakdown and the glycerol from fat breakdown.
Right. But here's the problem. At the same time, the adipose tissue is panicking and flooding the system with massive amounts of fatty acids to fuel the muscles. The liver is taking up these fats to burn for its own energy needs, but it gets overwhelmed. The sheer volume of incoming fat is too much.
And this is the turning point that leads to ketosis.
This is it. The liver is processing so much fat that it produces its byproduct, acetyl-CoA, much faster than its furnace. The citric acid cycle can handle it. It's like trying to pour a gallon of water through a tiny funnel. The funnel overflows. That overflow of acetyl-CoA is diverted into making ketone bodies.
Now, people hear ketones and they immediately think of the keto diet. Is this a dangerous state to be in?
In controlled starvation, it's actually a brilliant life-saving adaptation. After a few days, the ketone levels in the blood rise high enough that the brain, the diva, finally relents and says, fine, I'll eat this stuff. The brain adapts its machinery to start using ketones for about 70% of its total energy needs.
Why is that so good?
Because it spares your muscle. If the brain is eating ketones, it needs less glucose. If it needs less glucose, the liver doesn't have to break down as much precious muscle protein to make that glucose. You stop burning the furniture to heat the house and start burning the massive reserves of fat in the basement. This is what allows humans to survive starvation for weeks instead of just a few days.
But then there's the dark side of this exact same mechanism, diabetes mellitus, specifically uncontrolled type 1 diabetes.
This is the ultimate tragic irony. Harper calls it starvation in the midst of plenty. In type 1 diabetes, the pancreas is destroyed, so you have no insulin. And without insulin, even though your blood is swimming in glucose hyperglycemia, the cells can't see it. The glucose transporters are locked in the garage.
So the cells are starving, even though there's food everywhere. The body thinks it's starving.
It thinks it's in the worst famine imaginable, so it panics. It triggers the exact same starvation response we just described, but on steroids. It's completely unregulated. The muscles break down protein like crazy, leading to wasting. The fat cells dump biblical amounts of fatty acids into the blood.
And this all leads to the life-threatening condition of diabetic ketoacidosis, or DKA. I want to do a really deep dive on the mechanism here.
Yeah.
Because Harper mentions a specific bottleneck involving a molecule called oxaloacetate. This is the part that I think always confuses medical students.
It is the most critical concept to understand in all of metabolic integration. Let's visualize the inside of a liver cell. You have a furnace, that's the citric acid cycle or the Krebs cycle. It's designed to burn fuel to make energy. To start the furnace, you need two things. You need fuel, which is acetyl-CoA, and you need a spark plug, which is oxaloacetate. They have to combine to get the fire started.
Okay, fuel and spark plug, acetyl-CoA and oxaloacetate.
In an untreated type 1 diabetic patient, you have a tsunami of fat coming into the liver. That gets turned into a massive, massive pile of fuel of acetyl-CoA. It's piling up at the door of the furnace.
So why doesn't it just burn? There's plenty of fuel.
Because the spark plug is missing. Remember, the liver thinks we are starving. Its #1 priority is to make glucose. And it turns out the main precursor for making new glucose is oxaloacetate. The liver is actively stealing the spark plugs from the furnace and using them as building blocks to make sugar.
Oh, I see it now. It's a resource conflict.
Okay.
You're cannibalizing the furnace to build the walls of the house.
You are cannibalizing the furnace. So the citric acid cycle grinds to a halt. The pile of acetyl-CoA has nowhere to go. It can't enter the cycle, so where does it go? It overflows massively into the ketone production pathway.
And unlike in simple starvation, where it's a controlled, regulated trickle of ketones.
In DKA, it is a fire hose. The regulation is gone. You produce these ketones, which are acidic, so fast that the body's buffering systems are completely overwhelmed. The pH of the blood starts to crash.
And Harper mentions the smell of the patient's breath.
Acetone. One of the 3 ketone bodies is acetone, which is volatile. It evaporates from the blood into the lungs, so you can literally smell it on the patient's breath. It's a sweet, fruity smell, almost like nail polish remover or rotting fruit. It's a classic clinical sign.
And at the same time, the kidneys are desperately trying to get rid of the excess sugar and ketones in the urine, which pulls huge amounts of water out of the body through osmosis.
So you have a devastating combination of severe metabolic acidosis plus profound dehydration.
Which leads to coma, and if untreated, death. It's a complete and total collapse of the economic system. And it just highlights why integration is so important. You can't just look at fat metabolism in a vacuum. You have to see how fat metabolism is completely dependent on carbohydrate metabolism, providing that oxaloacetate spark plug. If one gear strips, the whole engine can explode. It really does highlight how precarious this balance is. We're all just these highly tuned engines walking a very fine tightrope every second of the day.
We are. We're regulating thousands of chemical reactions per second just to stay in that dynamic, non-equilibrium steady state.
So let's bring it all home. Let's synthesize this. We started with the burning candle, the torch of life.
And we've learned that we are indeed burning, but it's a slow, controlled, isothermal burn. We use the exquisite specificity of enzymes to lower those activation energy barriers exactly when and where we need to. We use ATP as the standardized currency to pay for order in a universe that craves chaos.
And we have this complex, beautiful trade agreement between our organs to manage different fuels under different conditions.
The liver, the brain, the muscle, the fat, they're all in constant communication.
I want to leave our listeners with a final provocative thought to chew on. We've spent this whole time talking about how brilliant and efficient this system is. It evolved over millions of years of scarcity, of feast and famine. We are genetically optimized to store fat for a winter that used to come every single year.
The thrifty gene hypothesis, yes.
Exactly. But now, for many of us in the developed world, winter never comes. We live in an eternal metabolic summer with an infinite supply of cheap glucose.
And that is the fundamental conflict of modern chronic disease. Our metabolic machinery isn't broken. In many ways, it's actually working too well. It's doing exactly what it evolved to do, store every excess calorie for a famine. But when the famine never arrives, that brilliant survival mechanism, that storage, becomes toxicity.
So things like obesity and type 2 diabetes, they aren't necessarily a broken system.
There are ancient survival mechanisms clashing with our modern, unnatural environment.
Yeah.
The machinery is perfect. It's just reacting logically to a context it was never designed for.
The machinery is perfect. The context has changed. That is a wrap for our deep dive into the introduction to metabolism. We really hope you look at your next meal a little differently, not just as food, but as a complex deposit into the most sophisticated economy on Earth.
And maybe spare a thought for your liver. It's working incredibly hard for you right now.
Absolutely. Thanks for listening. We really encourage you to dive into the Leninger and Harper chapters to see the actual chemical maps of these cities we discussed today. We'll see you on the next deep dive.